view about how things should. Oh,
how things should go in what?
at the iTerm.
Yes, yeah.
But
yes.
we're being recorded, so it's being. I'm going to turn off.
Yes. Okay.
Maybe after the talk you can discuss. So Professor Prasad, maybe you can start by introducing the speaker.
Yes, yes. No, I will do that. I mean, I'm waiting for 7 o'clock. It is still 1 minute left, and maybe I should wait for 1 more minute just so that anybody who is starting at 7 o'clock gets to attend the lecture. All right, so it is 7:01. I'm very pleased to introduce Barinder Banwait, presently at Heidelberg, who will speak to us on modularity over C implies modularity over Q. Barinder, please go ahead and begin your lecture. Thank you.
Okay. Okay. So thank you, Professor Prasad, for the introduction, and I'd like to thank the organizers and I guess Dipendra for the invitation to speak in this very interesting trimester. This is going to be an expository talk, and I'll explain what exactly the goal is in this first section, the introduction. So let's recall from Shonak's talk, this the modularity theorem version XC, which is what it was called in that talk. This is also how it's called in the book by Diamond and Sherman. So if you have a complex elliptic curve E, whose J invariant is rational, so I mean it's basically an elliptic curve of a Q, but like we're pretending it's over the complex numbers. Then there is some integer n, such that there is a surjective holomorphic map of compact Riemann surfaces from the modular curve x naught n onto C. So there was this version. There was another version in that talk, or I think it was the talk after Shauna gave 2 talks, namely a version XQ. And this is the one that actually has direct arithmetic applications, and the one that Wiles actually proves. So this is where you actually start with an elliptic curve of a Q, and then for some positive integer n, there is a surjective map of algebraic curves this time. So from x naught n to E. So here we are regarding x naught n as with this algebraic structure, whereas here we're just regarding it as a Riemann surface, compact. And the point of this talk is to show that these two notions of modularity are equivalent. So that's what the main part of the talk is going to be, this section 2, the proof. And then the final section is going to be some open questions about how to extend this notion of modularity. So we'll get there. Now, firstly, observe that by base change, like an elliptic curve of a Q is clearly an elliptic curve over any extension. If you have modularity over Q, then you can base extend this. And so we have the clear implication of the version XQ implying XC. So actually, the whole point of the proof is to go the other way. Why does modularity over C imply modularity over Q? And so the details of this, so I followed the the appendix to an article of Mazur. So this was an expository article, number theory as gadfly, but the appendix has some quite technical details. So
you mean if the elliptic curve over Q is modular, then it would be modular over any number field extension?
Yes, that's right. Yeah, like, so if you have this as a map over Q, then you can base extend this to any number field, and in particular over the complex numbers, and then you will get this version.
I think this would be non-trivial to define this version over any number field, like over totally real number field.
No, but so sorry. We are always starting with the elliptic curve as being over Q. I'm not saying that we can replace Q by any number field. I'm saying so Q is fixed, but we can take this map and base extend. So we can regard this as being over any arbitrary field. That's all I'm saying here. That's all I'm saying.
Okay.
So yeah, the details will be I'm following are in this article of Mazur in the appendix, and yeah. So the long story short, it is possible to do this, but with a possibly different value of n. So before getting into the proof, let me just set up some objects. So E is going to be an elliptic curve over Q. So yeah, by the way, Dipendra, like in the final section, we will start thinking a little bit about what modularity might mean for a general base field. But yeah, for most of this talk, E is going to be defined over Q. And L is going to be so here L is an arbitrary extension, field extension. It can even be the complex numbers here. So n is going to be an integer, and by x of n, we mean the modular curve of full level structure. So this is associated to the congruent subgroup gamma of n. So the matrices in SL2Z that are congruent to the identity matrix, modular n. And so also we have x naught n associated to this congruent subgroup gamma 0 n. And we regard these as algebraic curves over Q. So we make this definition. So the elliptic, so we say that E is modular over L if there is an integer n and a non-constant map from x of n to E, which is rational over L. And yeah, so observe here that this definition uses x of n and not x naught of n, which is what the first slide was using. Now, since we have this inclusion of congruent subgroups, gamma n in gamma 0 n, we have a map from xn to x naught n. And the result that we're going to prove in this next section, is the following result of Mazur, which is that E is modular, this elliptic curve E over Q is modular over L if and only if it is modular over Q. And actually more specifically, this modular map from xn to E will actually factor through this smaller modular curve x0n. So this is what we are going to prove. But before getting into the details here, are there any questions?
Can I just look at the slide again?
Yeah.
You said it is modular over L if there is an integer n and a non. Okay, good.
Yeah. Okay.
I just want to confirm one thing.
Sure.
So this xn with full level n structure, that's also defined over Q, right? For all n.
Yeah.
I mean, it should be, otherwise you cannot extend.
Yes, I guess it can be given a model over Q, but then I believe it is geometrically disconnected there. So I think if you go over Q zeta n, then it becomes connected. I guess, yeah, or there might be, this follows from this bilinear Rappaport interpretation of that modular curve. So, yeah.
But in your definition of modular over L, you need xn, you are base extending xn from what to L? I mean, you need that to be defined over Q, right?
Yes, yes, indeed. Yes. So for me, I'm taking this to be over Q, indeed. So yeah, so I'm foregoing geometrically connectedness for that. I believe that is Mihir, right?
Yeah.
Yeah. Hi. Okay. Right. Okay. So let's get into the details then. So yeah, again, I said this earlier. So if E is modular over a given field, then by base changing the map, it becomes modular over an extension field. And because these curves, all of our curves are algebraic, you don't actually need to go up to the complex numbers, but like any algebraically closed field is enough. So if it's modular over C, then it is modular over Q bar. So actually, what one really needs to prove is that if it's modular over Q bar, then it is modular over Q. Okay, so at this point, so most of the proof I want to focus on the non-CM case. So the elliptic curve E may or may not have complex multiplication over Q bar. And now, if it does have complex multiplication, then this was proved that this is true was proved in a paper of Shimura on elliptic curves with complex multiplication as factors of the Jacobian of modular function fields. So this uses a kind of more the ideas of the Hecker Größencharakters and zeta functions. I felt that I did not have time to go into the details of that as well. So the CM case I'm not treating here. So from now on, we're going to assume that E does not have complex multiplication over Q bar. Okay, so we are assuming that this is modular over Q bar. So we have a Q bar rational map from the full modular curve x of n to E. And the first step is to replace this x of n by x1 of n. Now, the way one does this is to consider what's called the conjugate congruent subgroup. So if you have any congruent subgroup gamma, I mean, for me, gamma is going to be gamma of n, then you can conjugate it by the matrix n001. This is not in SF2Z, but that doesn't matter. When you do this, you get this congruent subgroup. So gamma 0 of n squared intersects gamma 1 of n. I mean, so if you just write this out, it's a simple calculation with, like, you take an arbitrary matrix A, B, C, D, you'll see that you put an n next to the C. So you're increasing the level of the bottom left, which is why you have gamma 0 of n squared. And then you still have that the diagonals are congruent to 1 modulo n. And this contains this congruent subgroup gamma 1 of n squared. So this containment therefore then gives us a map between these modular curves, x1 of n squared to x of gamma tilde. But the point is that we haven't really done anything to go from x of gamma tilde to x of gamma. In a sense, all you've done is replaced the coordinate in the upper half plane by n times that coordinate. So you get an isomorphic curve. And in particular, so by doing this, we replace this x of n by possibly x1 of n squared. And we say possibly because it could already be that x of n to E factors through x1 of n. And indeed, I mean, that is, since we now know this is all true, like that's going to happen. But in the proof, we don't know that at this point. So that's why possibly one may have to go up to level n squared. And then we get an L rational map from x1 of n to E. So we are possibly replacing n here. So the n might have become n squared in this equation here. And also, like, because these are algebraic curves, and I suppose you could think of them concretely as models. One does not need to go all the way up to Q bar, but that there is always going to be a finite number. There is going to be a finite extension of Q over which this is rational, and then you could take the Galois closure of that if it is not Galois. So one will obtain a finite Galois extension of Q, L, over which one has modularity. And the point now is to go from modularity over this finite Galois L to modularity over Q. Okay, so let's let G be the Galois group of L over Q. So we now pass to the Jacobians. So we had a map of curves, and we're now going to, so this induces a map on the Jacobians. So J1n to E, all rational over L. So this is a homomorphism of abelian varieties. Now, so this J1n, this factors as a up to isogeny as a direct product of simple abelian varieties AF corresponding to weight 2 new forms of level gamma 1n. So putting that into this equation, we get this. So we're taking a product over these new forms AF, but we are in this equation we are regarding everything over L. So we have this homomorphism over L. Now, what we're going to do next is take the very restriction of this down to Q. Before we do that, just to recap that these objects E and AF, these abelian varieties, they're actually all defined over Q. But what we've done is we've pretended that everything is defined over L. And now we're going to take the very restriction back down again. So when one does this, like going up and coming back down, this kind of construction is sometimes known as Serre's tensor construction. So the details of this, the earliest reference I was able to find for this is this 1972 paper of Milne in Invenciones on the arithmetic of abelian varieties. And you get these, what you end up getting are these, you get these twisted abelian varieties. You're twisting by representations. So on the right, you're going to get, so you are twisting by the regular representation of G. So by which I denote by Q square brackets G. So we have this, we have this equation here, which I've just taken here. Now, let's consider the left-hand side here. So each of these AFs, these abelian varieties associated to the new form F, each of these over Q arises as a simple factor of this. That's just because the regular representation contains a copy of each of the irreducible representations, in particular the trivial representation. So this is going to contain each of the AFs up to isogeny. So we are technically we are working in the category of abelian varieties up to isogeny here, which is sufficient for our purposes. So in particular, AF must then also it can be identified with a simple factor on the right-hand side. Okay. But what do those look like? How can we identify the simple parts of the right-hand side here? So these will break up to isogeny as products of twists of E by each of the irreducible representations in Q square brackets G. So we always have that decomposition by writing out QG, so like E tensor, I don't know, R product over all of the irreducible representations R of G. But the thing is that they may not be simple over Q a priori. But in this case, they are, basically because E, again, does not have complex multiplication. So yeah, the details of this can be quite subtle. So there were papers of Everett Howe who looked into this question, and this was explained to me by Alex Bartle in this paper, Simplicity of Twists of Abelian Varieties. So in this case, we can conclude that each of the AFs that arise on the left-hand side can be identified with an E tensor M. So where we are twisting the elliptic curve E by an irreducible representation M. Which you can also think of as an irreducible QG module. Okay, so that's
Barinder, can you explain what does E tensor M mean? What kind of object is this?
Yeah, so this is an abelian variety. So it is the construction is, one can see this in Milne's paper. So it is an object that represents a certain functor of points. You can think of this as
E direct sum E as many copies as the dimension of M over Q.
Yes, yes, exactly. The dimension of these objects will be the dimension of E times the dimension of M. Exactly. I mean,
isogeny, it is that abelian variety.
Yes, exactly. And if you want to do this up to isomorphism, then one has to take ZG modules here and consider integral representations. It becomes a bit more subtle. But yes, indeed, up to isogeny, it is this object. And that's kind of why we are working in the category of abelian varieties up to isogeny, so that we can get away with just looking at rational representations rather than integral representations. But yeah, so this is an abelian variety that you can identify with the Weil restriction. Like I say, when the Weil restriction of the base change. Yeah, okay, so proceeding with the proof, we take this, so this is a key part of the proof, which, so, I mean, if there are any questions about this, then it's definitely worth it's definitely worth spending time on this, I think.
These abelian varieties on the two sides are not Q simple.
So the one on the left is AF is Q simple. So that's coming up in here. So we'll get there slowly. And on the right, well, since it's isogenous to something that's Q simple, then in this case it is Q simple, although a priori it does not have to be. Yeah, the general construction does not give you a Q simple abelian variety. Yeah, so I was saying this in answer to, I think, Professor Prasad's question. The dimension, so I was saying this next bit. The dimension of this, this E tensor M is the dimension of E times the dimension of M as a Q vector space. But the dimension of E is 1, so it's just this. And on the other hand, we know that the dimension of these abelian varieties associated to F is equal to the degree of the field extension of the Fourier coefficient field of F. So yeah, since F is a new form, the Fourier coefficients will generate a number field. That's not an obvious fact. You have to work to get that. And so the degree of that over Q, this is the same as the dimension of AF. And so therefore we get this equality. Like the dimension of the representation is equal to the degree of this Hecker coefficient field. Okay, so that's one ingredient, and then another ingredient from a paper of Ribbert in the 70s, I think, is that the endomorphism algebra of these AFs, so the endomorphism ring tensored with Q, is equal to this this Fourier coefficient field, and this is this is a field. So in particular, this is AF is simple over Q, not necessarily over Q bar. So we then have the following equation. So the endomorphism algebra of AF by this isogeny here, this is then equal to the endomorphism algebra of this tensor product. This twisted elliptic curve basically. And then we have that this is equal to F by Ribbert's theorem. And this embeds into this larger endomorphism algebra, where we regard E as being an elliptic curve over L. But again, we're going to use that E does not have any complex multiplication. So the endomorphism, well, E doesn't have any endomorphisms at all over Q bar. So we can basically forget this in the endomorphism algebra because it's just Q. So you will get like Q tensor M. So we then get that F is contained in the endomorphism ring of M. So here we are regarding M as a Q vector space, but we've just shown that it admits an action of F. So we can think of M as also an F vector space. But then what is what is then the dimension of that? So this equation here shows us that actually it has dimension 1 as an F vector space. Okay. Perhaps I should have said at the so at this point, what we're trying to do at this point is understand M. We're trying to understand M as a representation. So we've now shown that M is at least as an F vector space. We haven't thought too much about the G action yet, but as an F vector space, it has dimension 1. So now we're going to take this object again, the endomorphism algebra of E base change to L twisted, and we just showed that it admits an action of F because F embeds into this. But we saw from earlier that it admits a G action. So I mean, M itself is a G module, and G acts on E over L. That's just the Galois action on the points on an elliptic curve, and so therefore it will act diagonally on each of the elementary symmetric tensors, and so it will then act on this twisted space, and these actions commute because the F action is rational over Q by so here F is exactly the Q endomorphisms of AF. So the F action and the G action on this commute. In other words, G acts on this M linearly over F. But because the dimension of M as an F vector space is 1, that's just saying that the G action is a one-dimensional representation. So M is one-dimensional as a G representation, and so the action can be expressed by simply a character, which we'll call Khare. So yeah, we are now understanding more about what this M is as a representation, and it's essentially given by this character Khare. So in order to finish, one wants to do something like this. I mean, so I'll first say that this is not to be taken literally for what I've written here. This is just to kind of give some motivation for what kind of object to look at. So like we had this equation, AF is isogynous over Q to this E tensor M, and like morally or loosely, M is Khare. I mean, it's not, but once you have this, you could try to say, well, let's take Chi inverse or Chi bar, and then you can like take it to the other side. And one is trying to express E as a modular abelian variety. And so what we're going to do in the rest of this proof is do this properly. But it does suggest looking at this object, the modular form F twisted by the Dirichlet, but by the Galois character Chi bar. So this is where you multiply each of the AN coefficients by chi bar of G. So yeah, so we consider this this modular form, the twisted modular form. This is a new form in this case, and to do this properly, one uses the Eichler-Shimura relations. So this relates how the Hecker operator at P acts in positive characteristic to how the Frobenius acts on the reduction of the abelian variety associated to psi. So we twist f by chi bar, we get psi, and so this is a new form, and one gets the abelian variety associated to this, and we apply the Eichler-Shimura to this, which relates TP to Frobenius action. Now TP acts via the AP Fourier coefficient, so AP psi, and Frobenius acts by Frobenius on the reduction is this looks like 1 plus P minus the number of points on the reduction. So provided P does not divide N here. So one gets this equality between this expression for the P's Fourier coefficient of psi. But this on the right hand side is just the APE value of so this is what's sometimes called APE. So you so once one has equality between the AP values for almost all P, one then has that the L-adic Galois representations associated to a psi on the left here and E on the right, they are isomorphic for all L. And then, so one could apply Falting's isogeny theorem at this point, but this was actually already known by earlier work of Ribert. We actually get a Q isogeny between A psi and E from the fact that the Galois representations are isomorphic. And since the Fourier coefficient field of A psi is Q, that means the Nebentypus of psi is trivial, because the Fourier coefficient field has to contain the values of the Nebentype. We get that A psi is actually a factor of not just J1n but of J0n, and then we can embed X0n into J0n via the Abel-Jacobi map, and we get this map that is rational over Q, and that's what we wanted. Like, we were trying to get, if I jump back to the statement, I guess it was, yeah, so we wanted to show in the end that we have a map over Q of X0n to E, and that's what we've ended up with here. So yeah, I mean, I think it's worth maybe pausing for questions at this point, because I think that was probably quite, there was a lot of details there.
So in Mazur's paper,
okay, Devendra is asking.
No, sir, you speak first.
There are many details. Can you say what is the key word?
Yeah,
so it's
okay.
the mapping from X1n, and are you saying that mapping already factors through X0n, or something else is happening?
Well, that is true. That does end up being true, but the how one proves that
So meaning any elliptic curve which appears in the Jacobian of x1n already appears in the Jacobian of x0n.
Yes, exactly. That's Mazur's statement in that we're trying to prove. And yeah, so it's, where does so to go from J1 to go from J1 to J0, that's happening right here at the end. So the only thing you need to say there is that the Nebentype is trivial. So like the space of cusp forms for gamma 1n, this has a Dirichlet character decomposition for characters from so maps from Z mod nz cross to C cross, and we just need to show that and the F2 gamma 0n, these are precisely the piece where that chi isotypical component is trivial. So chi should be trivial there. And so if you can show that this new form, this new form psi that we've identified, if we can show that that has trivial Nebentype, then it must already be coming from gamma 0 of n. And that's true because we say that the Fourier coefficient field has to be, is Q. And why is that? Because, well, it contains, so the Fourier coefficient field is generated by these AP psi values, which we said was equal to these APE values. And APE is just P plus 1 minus some number. So these are all integers. So these are all rational. And so this field, the Fourier coefficient field is Q. And that means that says that the Nebentype has to be trivial. Because if it was non-trivial, then those the values would have to be inside the Fourier coefficient field.
But the Nebentypes can be plus minus 1, which belongs to Q. That's not an option.
Okay, so it could be the Dirichlet character of order 2.
Yeah, could be.
That's okay. It's just a twist of the original elliptic curve.
That would be a quadratic twist.
Yeah.
Yeah.
But if the character has order 2, then it's...
But that would not say that E is modular, but E quadratic twist is modular. I mean, there is some issue there, no?
Yeah, it does look like.
I think that what happens is that there's a lemma of Shimura's that if you have a modular form and you twist it, you get a modular form, but possibly a higher level, which is related to.
Right. So no,
character.
but something needs to be proven there. I mean,
yeah.
So I think my question would be, why cannot the Jacobian J1n be product of elliptic curves? Because suppose it is a product of distinct elliptic curves,
yeah,
then it has more things than coming from x0n. And to account for those more things, maybe you need to go to x0 of something more, as Arma is suggesting.
Yes.
They are not coming from that x0n, but it is coming from some x0n and that quadratic character and square of that modulus.
Right. Yeah. Okay. So yeah, it's true. Yeah.
So
I think the more
not
details.
saying that a elliptic curve, which is a quotient of x1n, is already a quotient of x0n, but rather it is a quotient of some x0n times m square.
Yes. Yeah.
Perhaps. Okay. All right.
Yes. Apologies for leaving out this key detail.
No, that's okay.
Okay, so if there are no other questions, then we could go on to the final section. So I was also asked by Dipendra to say a few things about this work of Chandrasekhar Khare. And this is about how one can extend the notion of modularity there are of course many ways of doing this, and for totally real fields, one can consider more general automorphic forms. But yeah, so the motivating question here, and for Khare in his article, was, so if you have elliptic curves over more general number fields, can they be modular in this sense of being dominated by x1n for some n? So River proved that if you have an elliptic curve over Q bar, which is modular in this sense, then E must be a Q curve. That is an elliptic curve that is isogynous to all of its Galois conjugates. And so this was proved in a paper of his in the 90s. And he also proved that the converse holds, assuming Serre's conjecture on modularity of mod P Galois representations, which we now know by the result of Khare and Fontaine-Berger. So Q curves are precisely the elliptic curves that are modular in this sense. So then that raises the question: if you have an elliptic curve over Q bar that is not a Q curve, then in what sense could it be modular? And here and for Khare in his article, we want to stay with this idea of being dominated by some kind of curve, like a modular curve. Yeah, so there are various approaches to this. So for totally real fields, one can consider Hilbert modular forms, and for imaginary quadratic fields, you have these Bianchi modular forms. But yeah, that's not what we're doing here. We're going to follow this paper of Khare, Belli parameterizations of elliptic curves and congruence defects. And so the idea of Khare there is to weaken the notion of congruent subgroup. So any congruent subgroup of SL2Z is a finite index subgroup. But the converse is not true. There are finite index subgroups that are not congruent subgroups. So he makes the following definition. So if you have an elliptic curve over Q bar, so a Belli parameterization of E, this is a non-constant map from, so you choose a subgroup gamma of SL2Z of finite index, so not necessarily congruence, and you say a Belli parameterization of E is a map from X gamma, the curve associated to this, to E, which is defined over Q bar, and you require that the zero cusp of this curve is sent to the origin, and we say that this gamma covers E. Now, if you have a subgroup gamma of finite index, then you want some notion of how far away from a congruent subgroup it is. So you define its congruence hull to be gamma upper C, to be the smallest congruent subgroup which contains gamma, and the congruence defect. So yeah, like how far away is it from being congruent? Is then the index of gamma and gamma C. And the congruence defect of an elliptic curve over Q bar is then the smallest congruence defect as you vary over all finite index subgroups gamma which cover it. So yeah, Khare was interested in these notions of congruence defect, and specifically how this varies. Like if you fix a number field and you vary over all of these curves, like what can happen there? So the first thing to say is that by a theorem of Belli, these parameterizations always exist. And so this invariant CDE is well defined, and it depends only on the Q bar isomorphism class of E. So it's a bit like the J invariant in that way. And so this was one of the two questions that Khare posed about this congruence defect. So yeah, if you fix a number field K, is there a constant CK such that as you vary over all elliptic curves over K, this congruence defect is uniformly bounded by this constant CK? So, I mean, so in the basic case of K equals Q, this is true by modularity. And indeed, it's just one, because we know that we have modularity in the congruent sense, not just in this Belly uniformization sense. But this is open for every other number field. Now, we also have from the previous slide that so what I was explaining about Ribet's article, that the elliptic curves with congruence defect 1 are precisely the Q curves. So Khare then makes this definition, so there's a typo there. So the Q field of an elliptic curve over Q bar is the fixed field of the absolute Galois group, which fixes the whole Q bar isogeny class of E. So this is Q. This Q field is Q precisely when E is a Q curve. And so a more refined question than the previous one, which is trying to replace Q curve with maybe other classes of like K curves perhaps or something. So if you have a number field K, then as you vary over all elliptic curves with that whose Q field is that number field, is the congruence defect uniformly bounded there? And this is also not known for any other number field apart from Q. So yeah, that was the end actually. So yeah, thank you for listening.
Thank you, Barinder, for a beautiful talk. Covering a large ground and bringing to some questions of interest, for doing research.
Okay, thank you.
How did you bring in the Belly's theorem on the previous slide? By a theorem of Belly, I am not fully getting that. So you are saying that such parameterization. So what is the parameterization being talked about?
These Belly parameterizations.
Yeah. What is that?
Yeah. Yeah. I'm not. I always have to confess at this point. I did not spend too much time with Khare's paper. So I don't know exactly which theorem of Belly is being referred to here.
Excuse me?
Actually,
yes,
Mazur defines.
It's simply of a statement that any curve defined over Q bar has a parameterization by a more general non-congruence subgroup. You know, as you can actually find it as a cover of P1 unramified outside of 0, 1, and infinity.
Is that the theorem of Belly?
P1 minus
yeah, that's the theorem of Belly.
Is just upper half plane mod SL2Z.
Yeah.
And then you look
and
at
this is just a particular case where you're taking an elliptic curve rather than a general curve over Q bar.
Oh, so Belly's theorem is more general.
Actually, yeah, if I may say, this is sort of interesting because it would find it finds the elliptic curves as pieces of Jacobians of these modular, instead of taking congruence groups, these Jacobians of non-congruent subgroups. Of course, it's an easy exercise to say that if you have an abelian variety defined over Q bar, I think it's a piece of a Jacobian of a curve, of a Billy curve.
Okay.
Yeah, so very interesting talk. Thank you.
Thank you, Armand. Thank you.
Actually, Mazur, if I remember, defines the modularity in terms of the hyperbolic uniformization, a specific hyperbolic uniformization coming from the certain congruent subgroups.
Yeah, for Mazur, that was, yeah, so he, I think, was working with X of n, so full congruent full level structure. Yeah, it's true that in the he does use the word hyperbolic, and yes, a hyperbolic uniformization of arithmetic type is, yeah, periodic with respect to a congruent subgroup. Yes, I believe that's equivalent to what I was doing in the first part of my talk. Except, yeah, I did not use the terminology hyperbolic uniformization, but I think that's subsumed in just saying that it's dominated by x1 of n.
Yeah, certainly, actually.
Given whatever you have exposed, do we know that a elliptic curve over, let's say, Q root 2 doesn't arise from a modular curve? Do we know?
So I think, well, so it's known that elliptic curves over totally real fields are modular now, but yeah, that's modularity in the Hilbert. Yes, that's a different notion of modularity. Yeah, I don't know. Yeah, so that would be the first case, I guess.
Not all elliptic curves over Q root 2 come from modular curve.
Is that known? Is it?
No, I'm asking, and I presume it must be true that not all elliptic curves over Q root 2 come from a modular curve, but I have no argument. No, I have not thought about this question.
Yeah, I'm
your
afraid
talk inspires one to ask such questions.
Yes, yes. Yeah, that's a good question. I also don't know the answer. Perhaps somebody else in the audience does. Has thought about this, or.
Well, there's a real divergence between modularity questions over in the higher dimensional case or over fields different from Q. You don't cover the elliptic curve. You only say that the L function is understood in terms of automorphic forms. So
so that's
I would guess that almost no. I think that would be the general situation, that an elliptic curve over Q root 2, for instance, while it's modular, is not covered by some simple modular
but
curve
of course, one wants to give a little more precise answer, no? Which elliptic curve over Q root 2 may still arise from a modular curve.
Or even just a concrete example of an elliptic curve over Q root 2, which is not covered by.
No, but if you base change the elliptic curve over Q to Q root 2, it does come. So yes. I think the best one could hope is that these elliptic curves are not Q isogenous. They are not Q elliptic curves.
Yes.
So
okay, so if you take
maybe does Ribet's theorem say it comes if and only if they are Q
Q curves.
curves?
Yes, yes. That is known now. So yeah, you'll take an elliptic curve of a Q root 2, which is not a Q curve, and that will be the first.
Maybe can you show that Ribet's slide?
Yeah. Yes, yeah. So the details are here. Yeah, it's not.
Ah, okay. So maybe this answers this. Ribet proved. Can elliptic curves over more general number fields be modular in the above sense of being dominated by x1n for some n? Yeah. So I think maybe Ribet answers that.
Okay, so any elliptic curve of a Q root 2 which is not a Q curve, then this cannot be dominated by a. This is not modular in this dominated mapping curve sense.
Yeah, it's if and only if. So I think this
Yes.
answers in a very satisfactory way.
Yeah, although then I suppose one could ask, does it have a belly covering instead? Like, is it dominated by a non-congruence?
Yeah, but that you said is always the case.
Yes, yeah.
That's always the case.
Yeah.
I mean, non-congruent subgroups.
Yeah.
Good. Any other questions, Devendra? You are going to ask something?
No, I asked that hyperbolic thing, hyperbolic uniformization thing.
Yeah, I can ask one question and I can look it up on internet, but what is Falting's isogeny theorem and how do you use it in the first part? I don't need that.
What is, sorry, Mihir.
Falting's isogeny theorem. Didn't you mention it in the proof of the first part?
The Falting's isogeny theorem.
Yeah, what is it?
So I was thinking of that as like for two abelian varieties A and B are isogenous over a number field K if and only if their L-adic Galois representations are isomorphic for one L and hence for all L. That's the way I have it in my mind. But I think I have the specific result that I was using, I can quickly pull up.
Okay.
Just bear with me. So I mean, in my case, actually, in this case, one doesn't actually need Falting's result. It was actually already proved for modular abelian varieties. So this is the result here. So this is from Ribet's paper, Twists of Modular Forms. This is the result that one has in mind. It's expressed as an isomorphism between homomorphisms between abelian varieties tensored with QL and homomorphisms between the L-adic tape modules.
Yeah, but okay. I mean, so on this slide, you have this AFQ isogenous to E tensor M, and from here you want to deduce that A psi is Q isogenous to E, right? And
yes,
there
exactly.
For that step, you use this Ribet's theorem or Falting's generalization.
Yeah, that's right. So if you know that the AP values are almost all the same, I think even density 1 might be enough there, then the L-adic L representations, all of them are isomorphic. Okay. And then that is equivalent to the statement that the abelian varieties are isogenous over the base field. But that this is true in general is a major theorem of Falting's.
Okay, thanks.
Right. Good. If there are no more questions, let's thank Barinder again, and maybe we end the meeting.
Yeah, thanks, Professor Prasad, for sharing this talk also on your birthday.
No, beautiful talk, and I'm very happy to have learned many things in this talk. Very nice, Barinder. Beautiful
Thank you.
maths and beautiful talk. Thank you.
Thank you
So
very
I
much,
think
Professor.
Okay,
I
sir.
leave now.
Yeah, by the way, can you end the meeting and in the live stream first
Yes, yes.
and in the recording also? Thanks.